to the AI by SMEs. People can still monitor and analyze them, but on behalf of people, from that year around, the AI will work on the monitoring. And based on that monitoring result, human beings will make a final decision and take a prompt action. So the role of AI and the human being will be changed in the page 3. So this is about the page 1. I'd like to share the current status of a smart factory expansion. When it comes to the smart factory, actually there are some companies who are having high level of a smart factory, or some are just having very basic level of the smart factory. So there are 5 different levels under the smart factory. Up until last year, about 12,600 Korean companies tried to introduce a smart factory to enhance their competitiveness. And from this year, we focus on platform to enhance their competitiveness more. This is our performance so far. We focus on the Korean SMEs in particular. Many of the SMEs are having the labor-intensive work, like a simple repetitive work or very dangerous work. We think about how we can make that kind of processes into smarter process. So from 2014 to last year, we work on the level 1 or 2, which is considered as very basic level of automation or smart factory. And from this year on, we have escalated our level from the basic to the intermediate. So that work have been collaborated by the central government and our agency of Cosmo and SME. Largely, if you look into the supply of a solution, MES takes up about 66%, the ERP takes up about 17%. So we largely focus on the supplying and expanding the solution. Based on that, the smarter factory will focus on the data collection, storage, and utilization. This is the current status of the manufacturing industry in Korea. If the manufacturing company want to make most of the smart factory, then the supplier should enhance their capability. But unfortunately, here in Korea, as of today, the supplier capability is still staying at the very basic level. So in the future, we try to encourage the suppliers to introduce level 3 or level 4 or 5. So we work with the startups to develop AI-based solution, and we distribute that developed AI solution to the SMEs, and we will provide the platform-based services for the SMEs. These are the key contexts. We try to turn the labor-intensive industry to the technology-intensive smart factory to enhance the quality of the employee's life. If we want to build a smart factory for the SMEs, but actually most of their work are largely labor-intensive. So all of the labor-intensive work should migrate into the smart factory. So we think about how we can make it happen. So the first thing is that we need to collect and store and analyze the data generated from that factory, and that will be moved to the clouding data. After a year, that AI technology or solution can be utilized to generate the basic pattern. Then we can generate an AI which is equivalent to 20-year experience, the skill level of human beings. So that AI will be distributed to the SMEs. So far I have shared what we have achieved from 2014 to 2019. We have worked with about 5,000 companies. For the process performances, productivity has increased by 30% and the quality has increased by 43%, and the cost has been cut by about 16%. And also for the smart factory, they have to hire additional about 3 people, so it generates a lot of beneficial effects. What we have to pay attention to is that the productivity has increased by 30%, but sales just to increase by 7.7%. We analyze why it happens. The Korean economy is largely run by large companies. So the large companies who are producing the finished products are receiving the components and parts from the partner companies who are largely SMEs. Even though the SMEs increasing their productivity throughout the smart factories, they do not have any chance to sell more, because if the large companies doesn't increase the total volume of a final product, so it's not directly linked. To resolve this issue, together with the Ministry of SMEs and Cosmo and with 19 technopark complexes, we try to figure out how the SMEs can make most of the increased productivity to find more the sales channels and to increase their sales. That is the framework we want to build. By doing so, there are suppliers and the manufacturing companies. There are many requirements and the difficulties we have listened from the other participating companies. The suppliers say that most of the suppliers are having a single solution. So if they are just having the single solution, they just go to the supplier. It's not easy to develop their sales capability. I mean, it's very difficult to find potential sales channel related to the startup. Startups largely engage in AR, VR, big data, and AI, and they are developing solutions based on the sophisticated technologies. Because they are not knowing about the manufacturing domain, even though they are having some technologies, since they do not have any understanding about the domain-specific expertise, so they cannot sell their products. And on top of that, the business owner of SMEs, MES, ERP, big database, AI solution, which will be introduced into their company, would be better if that's packaged into one. Then they can secure interoperability and information exchanges. So they can just deal with only one company. So they want to have one single total solution. So they want to have some smart factory supplier who can provide one single total solution. But in reality, Korean large companies are not that much willing to provide the total solutions for SMEs because it's not economically feasible. So that is the difficulties we are facing. In terms of manufacturing companies, they don't know what company is the relevant candidate to provide them with the most beneficial and most appropriate solution. SMEs are having strengths in manufacturing and fabricating than modeling. So when we are designing an engineering system, the SME should take part in, but because of their shortages or inadequate capabilities, they can't take part in that engineering process. So when it's installed at their factory, they just ask some specification or requirement to the developer, so that's another difficulties. So each of them are having different difficulties to introduce a smart factory. So we are there to resolve this issue. So we think about the total solution provider. So total solution So all the different solution provider standing from the level 1 to level 5 can organize SPC or M&A or alliance so they can work together to build a single total solution. If they achieve that kind of structure, then we can also working with the larger companies depending on some industry and the central government and the central government to give that alliances a priority right to the government-led project. So we are just having this kind of supporting scheme to develop the total solution. So from this year, we are building CAMP, so clouding-based platform. So every company can send all the information to the clouding platform, and inside the cloud platform, there will be some rooms per each company. Then they can make most of their data. That's the infrastructure that we are building, and that has been completed by just the last month. So it is called CAMP, Korea AI-based manufacturing platform. This is one single infrastructure. The manufacturing companies, a supplier, and solution provider, whether they are venture or startup, and some R&D center or the universities and other related stakeholders can come up on the camp to make most of the data to develop new solution and to verify that solution, and we can spread that solution. And that solution, which is proven here in Korean market, will be sold to the global market. That's our big picture. So it has been promoted from this year. So throughout the camp, about 69,000 SMEs will tapping on this camp to make additional economic revenues. When you are building the platform, suppliers and the manufacturing companies need to meet certain prerequisites. For the small and medium manufacturing companies, the older solution should be moved to the clouding computer, and the security on the clouding computer should be much stronger than the one in their IT room. Otherwise, their secret and their know-how will be open to everyone. So that's a big issue. So the security on the clouding computing should be strengthened on the camp. And that should be cost efficient, and they can save the cost by using the clouding, and they can easily exchange the information if they want to. And all the data on the clouding are owned by each company. And the software developers, there is a pass on the platform, and that's a runtime library, which is AI library, or data pre-processing and post-processing, and all the analytics will be provided at the pass. Then the startups can develop the solution for each different SMEs. For example, predictive maintenance solution or quality prediction solution. Then they can utilize runtime library and API provided by the platform. They can shorten the development time and spread it to the SMEs. So we need to meet these two prerequisites. Then, in the future, SMEs doesn't need to have their own IT room in their factory. What they need to have is just a PC to communicate with the cloud and the 5G network. Once they just have a 5G network and the computer to communicate with the cloud and computer, then they don't need to build and invest a lot to have an IT room in their factory. And if they have a big data center in the clouding for a year, then to enhance data value, the domain experts or the DT, OT, and IT will work together as a pair to analyze the data of the manufacturing company to develop or find the solution they want. Then the solution provider can provide the POC. And the consulting will take about 20 million won, and POC will take about 50 million Korean won. Throughout that investment, we will support SMEs to create additional value by using their data. And the government will support 200 million won for the level 1. And if it's level 2 or 3, then they will get the bigger subsidies from the government. By doing so, SMEs can take their competitiveness to the next level. So far, 12,660 companies have introduced the ERP or MES. Then their software are migrated into the platform. And the other companies who try to introduce that system, then they can move on to the clouding platform without any IT room in their factory. So ERP, MES, or PLM will be operating on the clouding platform. Then they can predict some abrupt malfunctioning or the quality. So that is the basic plan to support SMEs. Then the Korean government, we will list the private platform operated by NHN or KT, and we will support the usage fee for 3 years. And if when Korean SMEs are largely operating and producing in global market, then they try to use Azure or Amazon or some domestic platform. They also are able to receive the government support just as much as the other domestic SMEs. So instead of their own IT room, they can use the clouding platform. At the same time, global companies can use Google, Amazon, or the Microsoft, and the Korean companies will use the hybrid computing. So by doing so, it can secure interoperability. As Dr. Gretek explained before, we also introduced IRX to share and exchange data between different platforms. As you are well aware, Korean New Deal said 5G AI-based factory will be extended to 1,000 by 2025. Out of 1,000, 800 AI solutions will be verified in Korea and sold to global markets. In general, when it comes to the platform, all the resources in my factory will go up to the clouding. Then how we can maintain our businesses, then we can sum it up into 4 different parts. First, as you can see in the bullet point 1, computer hardware of SMEs and AI solution and big database will go up the cloud together with the ERP. Then the accounting and the operation know-how are going on the cloud. And on the cloud, every pieces of information will be open to everyone. So the security should be much enhanced. And the ownership of that all data belong to the owner of the SME, so it's much more efficient to operate. That's the one biggest benefit. If you utilize cloud computing, then between the suppliers, their production or sales planning can be exchanged in real time, or quality information will be shared in real time so they can enhance the productivity and yield rate. Of course, they need to reach an agreement in advance to enhance the profitability, and that's data sharing. And the manufacturing data can be shared very easily on the clouding, so we can create some synergy effect. Another thing is that CAC machine, robot injection machine, AGV, owned by the SMEs, should be maintained. Instead of maintained by the SME, it would be better to be maintained by the manufacturer of that equipment, and they can do that maintenance remotely once we are moving on to the cloud. And we can also do some predictive maintenance. That kind of business model is possible on this platform. Last but not least, when SMEs are saving their data on the clouding, they can use that data to create more profit, and the university or research center to use that to develop new solution or new algorithm. That means they can sell the data after they are signing on the security agreement or NDA. Then all the real data of the SME will be used to develop new algorithm or new solution. So their enterprise value is not based on hardware anymore. It will be based on the data. So if you just to collect all that well-defined data, then that is another source of revenue in the future. Last but not least, I'd like to share some project that we are operating together with the LNA I 4.0, and when we are migrating all the information to the cloud in computer, that we have a lot of sensing machines. So the attributes and the properties and the frequency of a collection and the units are all different. If that's the case, even though we are developing solutions, it's very difficult to apply them. So together with the collaboration with Germany, we, as you can see on the screen, to make a real digitalization, all the manual work in the production, all the solutions should be utilized to make every equipment automatic. And over that automation, all that data, the low data from the production equipment should be controlled by 100 milli per second. And if we store and collect all the data on the clouding, we call it digitalization. Of course, the digitalization starts from engineering and modeling first. But if we try to digitalize the existing equipment, then we start from the all that data that are input or migrated into the clouding. Then how we can store that digitalized data? All the data measured from the equipment on the production site, they had to fill out the Aas template, and we create a structure of the data by each different equipment. Then they can communicate between clouding and between the structure. And we try to develop the guideline and develop solutions, and then other SMEs will receive it and follow the manual to develop the digital, to achieve the full digitalization. Then we will have 3 deliverables. The first is how the properties, we need to define the properties and the frequency of collection. So all the equipment around the country should be collected in the same format. So the first thing is the guide manual that we will develop. That is the first deliverable. The second is from the PLC on the site, we are going to the cloud server to the time series data. So this is the second is OPC UA software. And the third is by using the collected data, when we are utilizing that collected data, at the end of this year to the early of next year, we will prepare the how to fill out AAS template. We will train that intensively, and when suppliers is saving the raw data of the SME, they will verify that content, and that verification will be done by the committee. Then that data will be saved onto the clouding platform. This is the real last part. We are living in the fourth industrial revolution era. We can't achieve it by alone. We are living in the super connected world. Otherwise, we cannot communicate if there is no interoperability. So we work together. We need to standardize first, and with that, LNI 4.0 conducted some tests. So we work with Germany to use their standardization. And when we are having Gaia X solution, then we cooperate with Germany. And also, together with the USA, there is an industrial IIC. We also develop a use case and test bed to see if our solution can be sold in the global market. And together with Japan also, for the future, everything will be operated by the robots. So the key in Japan is that the core part of a robot should be manufactured in Japan and sold to the global market. That is so-called RRI, Robot Innovation Initiatives. That is led by a Tokyo-based company with other Japanese companies. Instead of other industries, they focus heavily on the robotics. Therefore, we need to make most of those technologies to apply a little further. That's the best way for us to survive. So we have to consider Japan, Germany, and USA, and we also work together with these countries to lead the future of a fourth industrial revolution together. That's it. That brings us. Thank you very much.
Thank you very much. Thank you very much, Mr. Park from the Cosmo. He introduced the use case and why AAS-based smart data storage system should be developed. He underlined the reason why we should develop that. Next, we have Mr. Kim Yu-chul, CEO of the Nestfield. He's going to tell us about the actual use case and how that was applied to the SMEs in South Korea. The topic is AAS-based cloud data collection and storage for SME. 30 minutes, Mr. Kim. My name is Kim Yu-chul, CEO of the Nestfield. Cosmo is leading the way so that we can build the cloud data collection and the storage project for the SME. And as of the September, the first pilot project was finished, and within the October or November, the second one will be finalized. First of all, let me tell you about the needs for this project. And I would like to give you a brief background about the AAS used for this project. Germany came up with a vision called the Vision 2030. This is the vision for the Industry 4.0. And the core concept is the autonomy. And to achieve the autonomy, interoperability, and the sustainability are the core pillars. And once we have the interoperability and sustainability, the autonomous manufacturing can be possible. Let me tell you why this project was started. Up until last year, we have completed lots of the smart factories. 12,666 units were completed, and we are planning to build additional 30,000 by 2022. What matters is currently we do not have the data standardization framework. Whenever we are doing the project, we need to invent the wheel. We need to work on the standardization once again. And there has been problem about the interoperability. And we faced a lot of challenges in the past, especially because of the maintenance. So when we bring the AAS standard, probably we can get over the difficulties and we can lay the foundation for using the advanced analytics such as AI. And we can lay the foundation for the data analytics and we can create additional values out of the foundation. I told you about the AAS. Let me give you a little bit more explanation about the AAS. To achieve the autonomy, which is the final goal of the Industry 4.0, you needed to have the advanced AI technology. However, before that, you needed to build a digital twin, the cyber physical system. To build the cyber physical system, you needed to do the mapping between the digital one and the physical one. And the core technology for doing that is AAS, which is based on the IEC 63278-1. It is targeting product production and it has complex ecosystem. So metadata is really important. So you need to have a container that can address all those data. And AAS should be able to express all assets related to the manufacturing from the design to the use. And also, the standard property will be used, which is defined by the CDD or the E-class, and the semantic compatibility will be granted. Self-description or the self-acts function is within the AAS. Between the AAS, the relationship can be expressed, and when you combine the AAS together, you can describe a bigger asset. It's like an application in your cell phone, which means it has openness, flexibility, and efficiency, just like an app ecosystem. So we can build the AAS ecosystem. And once you build the meta model for the AAS, it can be utilized multiple times for multiple purposes. That is the biggest advantage of the AAS meta model. Once the AAS model can be made, it can be used for the XML JSON. Also, it can be used for the OPC UA, which is the industrial communication standard. And also automation ML for the interoperability for the engineering. And also it can be transformed into RWF for further analysis. And for the further information about the AAS, you can see these documentations. AAS standard documentation. And Germany, Platform Industry 4.0 homepage provides a lot of information, especially the details of the asset administration shell is a useful information to refer to. And RAMI model and the Industry 4.0 is fully explained in a book. And you can buy this book in Amazon. The Korean translated version will become available soon in November or December. Let me tell you a little bit more about the solution we are proposing. And we have 5 detailed tasks, as you can see on the left side. The first 3 steps are related to the development and developing the solution packaging. And the next 2 steps are the application, the pilot running in the field. And the next step is the dissemination and training and building the guidelines. For the solution development, we are not inventing the wheel. We have the existing technology I would say we just to integrate the existing technology as a single package. Aas data collection system was developed and the data collection system was verified. The second one is based on the Aas data. We wanted to put that onto the cloud. So cloud platform data collection and storage system was developed. To collect the data from the field, the edge data communication system was created based on the Aas. Let me tell you one by one. Aas standard-based collection system development. And there have been 3 steps. The first one is building the common data definition of the Aas template and how we can build the Aas meta model, and we developed the framework. And the second one is, and we targeted the pilot factory, and we started to build the template for each of the equipment within the factory. And also, as a last step, we verify the interoperability. As you can see on the left diagram, there are 3 layers. The bottom line is the robots. And the field data will be collected. Through the communication protocols and especially through the OPC UA protocol, the data will be collected. And the data will be collected to the OPC UA aggregation server. After that, the data will be passed to the cloud. Through the OPC UA communication, the data will be pulled to the cloud. All those database will be built based on the Aas data model. So we have no problem in data communication. On the right side, you can see Aas has a lot of the subset, and we can express a lot of the subset. The core subsets are, as you can see, identification. The first identification is literally the identification for the asset within the Aas. And the operation data is information related to the actual operation of the asset. Technical data is covering the engineering and the specifications information, and the documentation contains drawings, specifications, manuals, and etc. Currently, we are focusing on the data operation. And technical and the document data will be covered in the next stage. And let me tell you how we are utilizing the Aas-based data. We have 6 steps. The first one is, we are going into the factory, and the first thing we need to do is to have the process and equipment analysis. The asset analysis is done. When you go to the factory, you can see the lines and processes, the facilities and equipment, and there are lots of parameters related to it. For each of the segments, you need to structure, and the so-called physical breakdown structure is really important to do the analysis. After that, you need to capture what kind of parameters and what kind of properties are within each of the segment. Then you can come up with the field data. The field data needs to be classified, and the regularity of the collection and the property needs to be clearly defined for the field data definition. The next step is Aas data model. On the step number 3, Aas data model will be implemented. For the interoperationality of the property, and we usually use the CDD or the E-class because they are the standard for the property. And the property within the data model will be defined. And the data model itself can be classified into factory, machine, and the components. That kind of breakdown of the hierarchy will be made. The tree structure will be made. This is just like the search function that you are using in your computer. Once the model is made, the next step is relatively easy. Once you have the meta model for the AAS, OPC-UA model can be created because there is an easy conversion. And we have the tool for the conversion to the OPC-UA. External interface is also made. XML, JSON, RDF interface will be available. So web-based interface will be provided. So we are providing XML, JSON interface. And also we are providing the OPC-UA model. Because when the data is stored in the database, you need to define the database table. So based on the AAS meta model, we have created a database table. Last but not least, the field data mapping isn't necessary. However, it cannot be automated. Database table can be automated. However, if the field was started from the AAS in the beginning, probably the field data mapping table can be automated. But if you are coming late, then for the field data mapping table, you need to create the model once again, and you need to map the field data to the AAS model once again. And that's going to be done on the step number 5. To make the step number 5 easier, the Excel format, the CSV format is used. So the structured property and the field data can be mapped one-on-one basis. And the collection period and the collection regularity and the frequency will be defined here as well. And based on the mapped table, it's going to be applied to the edge area. Once this is done, the data from the field to the cloud will be automatically collected. So Cloud DB and the real-time DB and the will be all stored on the HDB. And the stored data and the real-time data and the edge data need to be utilized. So if you store all those data, the scalability will become really easy. So within our pilot project, and we put the graph and the 3D dashboard functionality within our pilot project. Let me tell you a little bit more about the cloud platform. What is really important is OPC-UA, which is holding the data at the edge. And this is a must. What is really important is how you build the AAS meta model and how that can be put into the cloud. And also the next step is how to convert the data model. And also there should be the editing functionality to look into the AAS structure and edit the structure. The last one is RESTful API should be there so that you can have the easy connection to the external systems. And even the edge, the core edge should be built based on the AAS. So we have the metadata for the edge. So the edge level document management can be done based on the AAS. As we are using microservices, we have created lots of services and interfaces, as you can see on the top left of the diagram. The reason we are using the microservices is because we do not want to have lots of the intervention for the existing system. The data is used in many places. So the TSDB and the config DB will provide the data to the lots of areas, so there will be internal message bus so that we can utilize the data easily. This is the Edge data communication system. You can see there are 3 blocks. On the top, you have the cloud platform. And at the bottom, there will be field data devices. There can be many types of the field data devices. And the one which is standardized is to support the OPC UA. And if you have the OPC UA communication, you can simply pull the data and it can be migrated from OPC UA to the AAS. However, in many of the cases, many of the devices does not have the information model yet. So to the OPC UA level, there are many implementation cases. So, as I told you, OPC UA needs to have the mapping between the AAS and the field devices. And if you are not using the OPC UA, there must be another process of the conversion and the mapping. And OPC UA aggregation part is really important. And on the Edge side, we needed to store the data for about 6 months. Even though we'll lose the connection to the cloud, we needed to build the local database so that we are not going to use any data. And I told you the Edge data can be designed based on the AAS, and aggregation and the mapping can be fully configured, and Edge data can be managed based on the AAS framework. We have cloud, Edge, and at the bottom we have the field systems. And we have AAS, cloud, and the Edge data system. We have 3 components. And I would like to tell you how it was applied to the pilot factory. Shin-woo. Shin-woo Kostak is one of the SMEs in Korea. This is the company which created the world's first 3D in-moldable PET molding machine. This company was unique. They are producing the machine and they are making the PET bottle out of the machine they produce. That's unique. So this is the optimal company for the AAS pilot project. So they were designated as the first pilot site, and the project was completed with great success. On the left side, you can see the equipment. This is the 3D in-moldable PET molding machine. And the blow machine, and there are injection machines. As I told you before, Edge gateway and the cloud system are common, and it should be common parts, and the mapping should be different among the companies. The top layer should be the same. And we built AAS with this machine. PET 3D IML AAS, injection machine AAS. So we have this kind of the breakdown structure. We'll build the AAS for each of the breakdown structure, and we'll build the property. The hierarchy level was company, factory building, equipment, module, and parts to parts. And sometimes we use the AAS, and if needed, we build the sub-model. Not only product, mold, and the label were included, and they were built into the AAS, which means the mold and the label will be interconnected within the AAS framework. This is the modeling outcome. Dr. Juyeon Lee will give you further explanation about the Aas modeling outcome. They have 14 assets, 19 submodels, and there are 40, around 408 properties for a machine. So this kind of modeling was completed, and they are in operation already. This is how the information was converted. After that, we did the mapping, and they are in production. The cloud is providing lots of tools. For example, once you have the AAS model, AASX package file is the outcome. And once you have the file and you can take a look into the file, you can see the assets, submodels, and all the properties. This is the tool which is developed in Germany as an open source program. AASX Package Browser is the open source tool you can utilize. And on the cloud, you can browse and edit the file. And we have developed another package browser for the AAS. So you can directly look into the file on the cloud. We added some of the services, and we have the data retention of the 6 months or 1 year. Once you have the 6 months or the 1 year of the database, you can take a look into the correlation. So we have this kind of graphic function, and also you have the history data check function so that you can see the history data and see the correlation. And 3D dashboard was implemented on our system so that you can see the various and the key components within the field. The so-called KPI factors were extracted, and you can have the visibility in the field on a real-time basis. The second pilot site is the Huon's, a pharmaceutical company. They will conduct the project in the future. They are relatively large, making the ample of vials and the tablets. And we are targeting the ample production line. We started to collect the data for the ample production line. And there are lots of steps. For example, like the weighting, sterilization, there will be breakdown for each of the steps, and they will be built into the AAS so that we can collect the data for each of the breakdown structure. Once the pilot project is finished by December, we needed to have the scale up, and we needed to disseminate this kind of project, and we needed to cooperate with the Germany. We'll build the interoperability verification committee already, and the Cosmo, Kitech, Hanyang University, and Aas Electric are the Korean counterparts, and from the German side, NNI 4.0 helped us a lot. And we are collaborating with the German experts for the standardization and the open source. And we are hosting this kind of forum together. And in the November, the Industry 4.0 book will be translated and be published. And once the Corona is gone, and we're going to have another conference. Currently, we are working on the pilot project, and we are going to build the guideline for the AAS application. And currently, we are working with the Korean Standard Agency. And we needed to distribute the standard documentation. Industry 4.0 book will be translated and published. In addition to that, we are going to distribute the standard guide document. Solution installation and operation guide documentation will be made and distributed. And training will be provided to the demand company and supplier companies. That's it from me. Thank you. Thank you, Mr. Kim. Thank you very much. And Mr. Park gave us the full explanation about the AAS and why that is necessary. And Mr. Kim told us about the actual pilot project within the Korean SMEs.
And now, Dr. Kim talked about AAS, that beta model should be built, then we are able to collect and store the data. Then how we can build a meta model based on the AAS? I think you wonder, or you want to know about that. So Dr. Lee Joo-young from Key Tech will make a presentation about that. Actually, she shows us some case studies how we can apply the meta model for the AAS. If you are new to AAS, then in the second session, the Dr. Dominic Lomas will give you the introduction and background of AAS. And he will also give you very specific technical characteristics of AAS. And Dr. Kim actually introduced the AAS for the Korean factory. So all the processes have been written down in the document. There will be developed as a guideline, and how we can do the OD interface and how we can realize the AAS that will be developed as a guideline. And after that, to realize the AAS, there will be some training and education for that. So don't worry if you are new to AAS. There will be a lot of programs waiting for you. In the future, if you really want to know about AAS and implement them in your actual working place, then there will be a lot of guideline documents and training for you to have tap on the AAS. So please refer to that. And I'd like to hand over the stage to Dr. Lee Joo-young. She will talk about the Aas model implementation method. Hello everyone, I am Lee Joo-young from Key Tech. Today I'd like to talk about how we can implement and apply the AAS to the domestic factory. By doing so, I will share some strategies to apply Aas model to the factories here in Korea. Let me just introduce you our agency of Korea Institute of Industry Technology. It is founded in 1989. We have main 3 research centers, one in Cheonan and the other in Ansan that I'm working for. And there is another one for studying root industry in Incheon. And we also have operations globally. We are kind of a combination of academic study and some actual implementation agency. So when it comes to the actual study concept and implementation, we studied to optimize it to the environment of the companies. So it's government-backed research center. The key of today is AAS. So let me just define the AAS first. So first, we need to understand why it is necessary. Most of the audiences who are listening to this presentation have ever heard about the digital transformation, cyber physical systems, and digital twin. Digital twin or cyber physical system is kind of to turn the physical entity into the virtual environment, but how to implement it and the scope are a little bit different. But the key of today is to tell the difference between the two, so we consider these two as a single same concept. So where have you heard about CPS? Actually, Smart Factory have 5 different stages. The highest level is advanced. CPS has been perfectly implemented. That's called advanced stage. Many large companies have put a lot of efforts to realize and implement the CPS. CPS is not a single concept, but it's a very, very big concept and a single paradigm. It's very difficult to define in a one sentence, but let me try. The concept of CPS is combining physical system and controlling computing element. It's network-based distributed control system. CPS is actually applied to the manufacturing environment, then that is called CPPS. That means some actuator and sensor or some of the production elements have become the network and intelligent, and that is key to the smart production implementation. There are 4M2E. You might familiar with the 4M, which stands for machine, man, material, and method. And for cyber, 4M data and model, and how we are delivering what information, when and where and why. These two are realizing the cyber production system. That means the equipment in the real environment will be transformed into the virtual environment, and throughout the communication system, these two will be synchronized. And the synchronized data will be analyzed before manufacturing or be verified afterward. That is CPPS. The CPPS is having three different characteristics. This is the same as the characteristics of the smart factory. First is connectivity. To realize the synchronize, everything should be connected seamlessly. The key of this connectivity is IoT. And the second is virtualization. The entity in the physical world should move to the physical and virtual environment. The first is 3D visualization is required. When it comes to the CPPS, someone only think about 3D visualization. It's very important, but it's not all about CPPS. That's just the basic and starting point. And the second stage is static data should be binded. The raw data from the site should be synchronized and verified on virtual environment. That's the second stage. And the third, virtualization, is not only deal with the data, but also behavior and dynamics of the entity can be realized throughout the mathematical information. That's the third stage of virtualization. If we realize these three, then we can achieve a third characteristics, which is intelligence. It learns the past behaviors and run the simulations and recognize the system behavior in advance and afterwards as well. It utilizes data analytics. The most important thing is that it's not simple, the realization in the virtual environment, but they have to provide the feedback to provide the controlling function to the real environment. The AAS that I'm trying to explain today is the very basic standardization to realize these three characteristics. So let me give you explanation about AAS. Before that, there is some object in physical world. And that is called asset in information world. Asset administration shell is that the one. And when we try to turn the object in the physical world into the asset in the information world, it's a collection of information that is mechanically processable manner. They have to have a unique identifier. If you look into the images on the right side, it's asset. A single document can be an asset. On the CPS that I'm defining is that at least it has a sensor and actuator. Controllable entities accessibility should be considered as an asset. And when you search through the asset, the blue area might be the area which has some intelligence. Asset, once AAS is created, then it has a unique identifier. So it has some function, and what mathematical is based on to run that function, and they also able to make a decision. The AAS has header, which has identification information, and the body, which is the collection of sub-modules. If you understand asset, let's go to the sub-model. I just very quickly touch upon the sub-models. Sub-model is kind of grouping and categorizing of information. For example, if you want to analyze energy-related information, then you can collect all the information related to the energy, and then you can create the energy sub-model. So sub-model is simply speaking grouping of the relevant information. So basically, 4 basic models included in sub-model. Identification, which is the unique identifier, and technical data, the basic specification and engineering information are included. And operation data includes the actual operation data when they run the asset, and document means all related data, including drawings and specifications. And this is the example of a sub-model. This is so-called common sub-model. It's a kind of a must for the sub-model to have. It doesn't relate to the domain specific. It's very basic, common sub-model. There will be a lot: configuration information, safety, security information, and many informations are grouped and categorized by a related area. And also you can also create the domain-specific sub-models like drilling, milling. You can collect all the information specific to the drilling or milling. So this is the big characteristics of sub-models. The property is the one element of the sub-model. Property has a unique identifier. It's very important. There is a length and width, and each of length and width are the unique identifier, because within the AAS, the unique identifier should be translated same meaning to all users. So we need to have a standard terminology dictionary. And if we are allocating the ID from that common dictionary, then everything can be translated into the same thing. And property has 2 different things: type and instance. Type means there is no value, instance has value. And the images on the right is the example of the property. There is an asset with an ID. There are 3 different properties: length, width, and height. So 3 properties are having a specific IRDI, and also you can add more properties to identify an asset. So these assets can be expressed by these 3 different properties. We talk about the standard dictionaries required to translate single things into the single meaning. So we are having 2 different common dictionaries. The first is IEC 61360 CDD, and the second is E-Class. We are using these 2 standards to allocate ID and properties. They include all the unique identifier. For example, AS, we can create AS for motor, and the sub-model is technical data, and under that there is a property which is the max rotation speed, and the property should have an IRDI. And how we can allocate the IRDI? We just open up the E-Class to find the max rotation speed. Then they just give us the same unit and same definition and same property ID. Then we are using that. By doing so, we can send the same messages to all the users by using the standard dictionary. So throughout the pilot, so I just give you the basic explanation about the concept and how we can do some modeling. And I just take some examples of past factory. First is planning, analyzing, modeling, and AAS implementing and testing are the 6 different stages. Planning means we need to understand the system that will implement AAS. The scope should be very specifically defined. If AS is about the design or quality or process, that should be very specifically defined. And also the purpose of AS is for the web monitoring or some advanced diagnosis or analysis. If that is for the analysis, then they need to have some other relevant parameters. And if AS is at the design of the whole life cycle or usage or operation, depending on that, even though the asset is the same, the data set underneath of the asset should be different. So we have to set the scope very specifically. That's very important. Second is analyzing. We can create the AAS for one single equipment. AAS is important, but the hardware and software and infrastructure should be understood. And based on that, we can collect the relevant data and analyze it. If the purpose of that, it's for the prediction and the diagnosis, and the data should be more, then we can include the activities that can analyze and diagnose the data more specifically. And the next is modeling. Actually, this stage is added when we are having this test. It seems very natural to have it, but when you are building the Aes model, not to define the modeling in detail, then sometimes we failed. If we have to design the asset first, what it means is that we are designing the asset structure. When you are looking at the one single equipment, the structure itself is very diverse. So depending on your purpose of the structure, you can put the different meaning to that. So first, we need to define the structure of the asset first. According to that, we can mapping the relevant data. As I mentioned earlier, it can include some parameters or some dynamics or mathematical information, and the relevant parameters will be included. Let alone the AAS, they have to understand asset itself, and then we can design an engineering AAS. Tools doesn't have a very specific UI, so when we are doing this test, we just to create our own technology to design the AAS. I will get back to that later. So the first is how we can define the asset, and we can define the relations between the asset and what is the sub-model, and how we can see the hierarchy of the sub-models and how the data will be mapped. That's what happens at the modeling stage. And then we are moving on to the implementation. When we are doing the implementation, AAS Package Explorer will be used to implement the AAS. In the process of implementation, it can happen at the modeling or implementation stage. The unique ID will be allocated. If you fail to find one from the standards, then you can define it newly. So this is the process you have to do at the implementation. And then we can turn that model into the officiated model, and that model will be implemented in the actual equipment. So the information should be delivered to the cloud. So we have to verify that the information is well flown to the platform. And the second thing is that whether it's compliant to the standards. This is the, let me just to show you one test case by each different stages. At the first planning, we developed a very simple AAS like modeling or the injecting. And actually this facilities is developed by this company. The goal is to have the monitoring. And depending on the life cycle, we focus on the operation only. This is the targeting and analyzing the asset. Synocostek equipment is the in 3D IML injection stretch blow. It has a three process. First is injection, and then the preform after injecting, they go through the reheating, and then they just blow to do some labeling. So the third is the stretchy blow, and the fourth is a takeout. We understand the process first, and then we get the structure related to the data. And the third stage is modeling the asset itself. The first, the thing you have checked is process, and this is about the whole structure and the logistical flow. All flows on the screen is not translated into asset. We just try to find one relevant to modeling the asset. Actually, injection module have defined the asset because injection is one of the most common asset and common characteristics that many of the Korean SMEs are using. So after this test pilot project, we develop a little further based on the injection. So we just break it down the injection module. And this is the field data we have received from the factory, and it is also technical information mapping. The product data, we didn't do some AAS for the product data. When we are having some other consortium, they did it. So after we are modeling the asset itself, then we have to go through the AAS modeling. It's not the complete version. We are doing it only for the only one factory. This will continuous work. And let me just give you how this format consists of. As you can see here, it's based on the Excel sheet because many people working in the factory are familiar with Excel, and it shows what is the asset and what kind of a hierarchy they are having, and what are the submodels and what are the properties. And the IRDI of the properties are mapping of the IRDI is also shown in the Excel sheet. Not only the IRDI, the unit of measure and the actual operation data, and every relevant informations are stored and input in single Excel sheet. The fifth stage is after modeling the AAS, we are implementing it to the one. So we have used the AAS Package Explorer. We have repeated this work a lot because of the trial and error. But finally, we can use this tool much easier compared to the one that we use it for the first time. There are two different versions, editing version and viewer version. If you use the editing version, you can easily mapping and define the relations. The last stage is implementation and system testing. System implementation and testing them. After we create the AAS, then it can be transferred to officiate model. And all the terminologies that we define and the data from the field are not correctly mapping. So we need to do some mapping work here. And after these two work, as Mr. Kim mentioned, within the system, all the data from the shop cloud to the cloud, the information will be delivered perfectly. And then our purpose is that real-time monitoring. So as you can see here, 3D-based real-time data monitoring is making possible. You can see 8 different equipment, and you can also see the very detailed videos also. On the screen, it shows 8 different equipments. The key KPI is shown in real time. The productivity and what alarm have been activated. And then if there is alarm activated, then the color changes into red and the operation suspended. So it's 3D based but visualize the screen. And the accumulated production can be maximized depending on the need of the user. And actually, this 3D visualization is not perfectly implemented. We are keep updating it, and we are still developing the best and optimized 3D visualized screen for the user. And it shows every information about the equipment in real time. This is the conclusion page. So the reason we are sharing this actual case is that I don't think you want to know specific cases of one single case. I think based on this experiences, you want to see what is the direction that we want to head towards. I'm not that much experienced, but I'd like to share some recommendations for you to develop it further. First, when we are designing the system, we need to design the scope and the candidate for the implementation. But the AAS itself, the scope is very wide, and if you want, then it actually can express everything. So from the modeling perspective, before you are doing the modeling, you have to define the subject and the candidate as much as possible. If you define it well, then you can make every stages easily without much change. And the second thing is that we just believe modeling. If we are done modeling, then everything will be done. But before having the asset modeling, the asset design itself needs to be required. The physical structure should be defined, and what data need to be input, and what kind of dynamics is required for that. After that, you can create the AAS. And the third is that the design guideline of AAS is required. Our moderator mentioned that there will be some guidelines prepared and some training session will be prepared in the future. But we need to have AAS design guideline and template. What is the asset and what is the AAS and what is the property? That's depending on the modeling designer. So whether they are compliant with the standards or their structure is efficient, then domain experts should get involved in that work. But sometimes that is limited. So we need to provide some guidelines for the people to lead the work to a certain degree. So we realize design guideline and template is very important. The fourth is that we use the AAX package explorer and also dictionary, which is a standard, the CDD, and E-class. At the very beginning, we didn't use these tools. We just used the very simple one. If you have the tools, but it's much easier to implement it. But still, there is a lot of issues like bugs. So it's not user-friendly. Very difficult to edit, very difficult to change. And CDD and E-class is not easy to find one. It's not easy to find the relevant properties. All different cases are possible. So the people who are doing the modeling should respond to the all different unexpected cases, but they need to work with experts. So all in all, I think the domain experts must take part in the whole process. Domain experts, if the asset is a facility, we need to have domain experts of the facility, but also some other area as well. And the facility itself and the system experts should take part in the whole process to model the AAS, then we can meet our goal throughout this AAS modeling. That's it. Thank you very much. Dr. Lee, thank you very much for your presentation. Let me just share some comments. Dr. Lee and President Kim have worked so far for about the past 1 year to develop and modeling AAS. They just began from nothing, so they are really trailblazers. So they just created some paths for the followers, and they will develop some guideline documents in the future. So these two people are trailblazers here in Korea, and they make some just presentations. They will share every information with you. And so if you're interested in the AAS, you will have a very clear and easy to understand guidelines. AAS seems very complex to some of you, but it's very difficult to create it at the very first trial. But once you develop it, you learn a lot, and also throughout the whole life cycle, from the developing and describing, and you can also communicate with other factories. That's very difficult at the first try, but once you have developed it, it's much easier. If you have one equipment at the very beginning, it's not easy to maintain it by yourself, but you are accustomed to it later on, just like that. We're going to have a 20-minute break. So during the break, the technology of AAS, once it is realized and implemented in the asset, then there is unlimited functions and applications will be created. So the pilot project was about the monitoring of the asset. And during the 20 minutes, we will show you one video. And Nestfield, together with Hanyang University, have plug and production realized that the factory based on AAS, if one equipment is out of order, then they just plug out that equipment and plug in other redundant equipment, and we have some demonstration system for that, and we created some demonstration video. We're gonna run that video during the 20-minute break. So have some break watching that video, and after the break time, Dr. Dominic Ramos, who is the expert in AAS, will give you background and the definition of AAS. Thank you.
This is e-demonstration system of Asset Administration Shell, AAS, based plug and produce P&P in smart manufacturing, co-developed by Nestfield Ltd. and Hanyang University. In the era of Industry 4.0, one of the key challenges is how to digitalize the industrial production. The Asset Administration Shell is designed to transform the asset from a physical world into a digital world. What is Asset Administration Shell? It is a virtual representation of all the information and functionalities of an asset. It provides a standardized communication interface for information exchange. It is an access point of information and value-added functions in Industry 4.0. Why is Asset Administration Shell needed? The purpose of Asset Administration Shell is to facilitate the exchange of asset-related data along the production system life cycle. The Asset Administration Shell will make all the manufacturing components interoperable to realize the autonomy of Industry 4.0. Adaptable Factory envisions a flexible factory where production lines can be reconfigured during runtime. Analogs to the plug-and-play concept for desktop computers. The vision of plug-and-produce use case is to enable plug-and-produce capabilities for future production facilities. Compared to today's traditional production, plug-and-produce makes a new production paradigm possible. If there is an error with the working robot, the production line will stop. Therefore, on-site operator will immediately plug out the error robot and plug in a new robot, which will connect to the production system and perform the same tasks. That is, new field devices or production modules shall be integrated into production lines with minimal overhead, thus greatly increasing the production flexibility. The AAS-based P&P demo system has a 3-layer architecture. The top decision-making layer controls the whole system running using a web UI. The middle AAS layer is the AAS platform supporting AAS information exchange. The field asset layer contains 3 type-independent industrial robots and 1 turntable. This is the demo for showing AAS, Asset Administration Shell-based plug and produce in smart manufacturing. AAS plays the same role as the digital twin in smart manufacturing. Key characteristics of this AAS-based P&P system are threefold. First, each asset, for example, robots and turntable, has a unique AAS. Second, asset information are digitally represented in the AAS. Third, AAS can communicate with each other to realize the P&P function. AAS is composed of Digital Factory Header, DF Header, Digital Factory Body, DF Body, and submodels. AAS is now under development as an international standard in IEC Project 63278. Asset information are stored as properties in the AAS submodels, and the AAS has a communication interface to exchange data with other AASs. This is the information model of the AAS for KUKA robot. The DF header contains basic AAS information, for example, identification of asset and identification of AAS. The ID is in a format of Global Unified Identifier. The DF body contains 5 submodels. They are 1. Index data item, 2. Property value statement, 3. Documentation, 4. Communication, 5. Pick and place. The pick and place submodel is an asset-specific submodel, which is designed for KUKA robot to store and exchange pick and place related process data. How to implement the AAS? First, we use Automation ML, standardized in IEC 62714, to model AAS information of the P&P system. Automation ML is an XML-based data format that is suitable for describing information in AAS submodels. Automation ML contains an instant hierarchy module, hierarchically modeling individual objects as internal elements. Second, we use OPC UA, standardized in IEC 62541, as the communication interface to exchange data between AASs. OPC UA is a machine-to-machine communication method, providing interfaces for data exchange between industrial assets. We adopt OPC UA client-server mode, to realize the communication capability of AAS. By utilizing Automation ML and OPC UA, AAS realizes the P&P capability in Industry 4.0. The turntable is surrounded by 3 robots, designated as R1, Epson 1 robot, R2, Epson 2 robot, and R3, KUKA robot. The web UI controls the system operating in operation mode and P&P mode separately. When an operation strategy is chosen on web UI, the system will run in an operation mode. First, click the drop-down menu to choose 2 robots, for example, Epson 1 robot and KUKA robot, to operate in the operation mode. Afterwards, Epson 1 robot and KUKA robot are executing the pick and place task on the turntable in an operation mode. Indicator lights of Epson 1 robot and KUKA robot are green, while the indicator light of the Epson 2 robot is red. Finally, real-time AAS data of robots and turntable are monitored on the Web UI real system. Operation is synchronized with the virtual animation on the Web UI. In order to let the system run in a P&P mode, click the P&P drop-down menu on Web UI to choose a P&P strategy. For example, plug out one running robot, for example, Epson 1 robot, and plug in the third idle robot, for example, Epson 2 robot, to proceed with the pick and place task. At this time, all indicator lights of the 3 robots turn to yellow, indicating the P&P configuration process among 3 robots and turntable. During this process, AAS of robots and turntable will communicate to determine the operation of corresponding assets. Now, KUKA robot and Epson 1 robot are working in an operation mode. Now, through P&P mode operation plugout, the Epson 1 robot plug in Epson 2 robot. Now Epson 1 robot is plugged out, Epson 2 robot and KUKA robot are executing the pick and place task on the turntable in a P&P mode. Finally, real-time AAS data of robots and turntable in the P&P mode are monitored on the Web UI. Real system operation in the P&P mode is synchronized with the virtual animation on the Web UI. In order to change the system to run in another P&P mode, click the P&P drop-down menu on Web UI to choose another P&P strategy. For example, plug out another running robot, the KUKA robot, and plug in the third idle robot, the Epson 1 robot, to proceed with the pick and place task. At this time, all indicator lights of the 3 robots turn to yellow, indicating the P&P configuration process among 3 robots and turntable. During this process, AAS of robots and turntable will communicate to determine the operation of corresponding assets. Epson 2 robot's status light, it turns green to signify movement. Now KUKA robot is plugged out. Epson 1 robot and Epson 2 robot are executing the pick and place task on the turntable in a P&P mode. The figure shows the sequence diagram illustrating the information flows among AASs. Following the diagram, robots and turntable can operate in accordance with the chosen P&P strategy. Initially, R1, R2, and turntable are operating in an operation mode. When a P&P strategy is selected on the Web UI, it will be delivered into all the AASs in the AAS platform. AAS of R1 will send its current status information of AAS of turntable, R2, and R3 sequentially. And AAS of R3 will order R3 not to operate anymore. After everything is confirmed, the PNP mode ends and the PNP strategy is carried out successfully. Finally, the AAS platform will feed updated information of all involved AASs back for showing on the web UI.
We'd like to begin the second session. So during the second session, we will have two presentations. The first presentation will be delivered by Dr. Dominic Lohumus, and he is the CTO of LNI 4.0. And this is the agency to verify and test the core technologies of Industry 4.0. So again, the Dr. Dominic Lohumus of the LNI 4.0 will deliver about the test beds for interoperability in a German-Korean setting. So he will make a presentation during the next 60 minutes. So there will be two translators. So please let the Dr. Dominic can be start any time from now on. Let's start. Dr. Dominic, are you ready? You can now.
Good. So it's my deep pleasure to work with you together and to have this international collaboration in this very, very good setting as we work together. In the upcoming hour, I will introduce the test bed on the asset administration shell in Germany. This test bed is located in Hanover. Hanover is in the northern part of Germany. Already on this first page, you see a kind of complexity within the organizations that are involved in this test bed. I will explain what you see here, and no worries on the complexity. I will explain to you what we mean by test bed, and I will explain how the partnering takes place. The test bed is about standardization. It is focusing on standardization. So this is the key where we are working on. We have partners. One partner is very important for us. This is the Deutsche Messe. This is the so-called Hanover Fair that you all know, and Professor Hong and other partners of Korea are there, President Park regularly. They have a branch in this Hanover Fair. It's called Academy, and this academy underlines the importance of education and upskilling with respect to Industry 4.0 and the asset administration shell. So this part is taken care by Deutsche Messe Technology Academy. Then and that is also very comparable to Korea, we need a partner who is there and who is the host. This is the so-called Competence Center 4.0, and I will come back to this in a few minutes. In Germany, it is very important that it is based on a very broad platform. Whenever we do something on a federal, national level, that immediately wants to be a global project or a global thing. So we have the German Platform Industry 4.0 and the Standardization Council. I will come back to those two organizations also in the next slides. And let me remark that the Standardization Council will give an own presentation after my presentation. And then we have industrial associations. They are the backbone of German industry and organizing broader topics in German industry. So this is the organization for machine building. This is the organization, the association for electrical, and this is the association for software. On this slide, you see a first round of testbed partners. This will grow. Until now, we had a large kickoff phase of this testbed. Unfortunately, the COVID-19 pandemic situation forced us to almost have 1 year of kickoff to collect all requirements in all areas. So we start in a very broad setup. And on the top part, you see all the partners that I introduced already. In the center part, you see requirement and and application partners that will use asset administration shell in all their areas. And that goes from mechanical all the way to low code environment, system integration, electronics, IoT, automotive, etc. You see, all small, medium enterprises are not only the technology consumers and application companies, they are on the same level also technology providers. So we have consumers and providers in a double role, to say, at once. This is possibly very special, but it gives us more perspectives on the topic. And then on the bottom part, you see the providers or the partners that are important for us, that are already mentioned by all wonderful presentations we had in the sessions before. Thank you very much to this excellent Nestfield presentation. Thank you very much to the excellent presentation of the PhD student that we just heard before. Excellent. And also thank you very, very much to the presentation of President Park of Cosmo, who gave a very good overview on the Korean perspective of Industry 4.0 and asset administration shell. You might wonder why we have two companies also down here. This is because key experts, leading experts of asset administration shell are in these companies. And OPC Foundation and also E-Class organization, beside Platform Industry 4.0 and Standardization Council, the Machine Building Association, the Electrical and the Software Association were already discussed severely in the last 2 hours. Nestfield presented already the vision for Industry 4.0, or how to say, when is Industry 4.0 finished? And it is really about interoperability, autonomy, including sovereignty. This is very important. So you could add also sovereignty, data sovereignty here. And that was already discussed in the last 2 hours intensively. Data sovereignty is the key to enable business, data-driven businesses. In the end, we have to earn money with this. And sustainability. And sustainability is more than climate change and pollution. It is also good work in a completely digitalized industrial economy, industrial setting, as we see it in Korea as well as in Germany. Both countries are extremely industrialized, rely on industrial production when it comes to their wealth, and are very, very comparable and very similar in terms of size, also in terms of the branches where industrial areas where industrial production takes place, and also in the way how they understand modern digitalized industrial production. These two countries fit extremely well when it comes to digitalization of industry. Also very important is the social participation. We have to have a society acceptance for what we do here and what we propose. We have to have all our workforce behind us. They have to somehow like it and understand it. This is extremely important. This slide shows a very complicated setup from your perspective, but it is somehow necessary. And I would like to briefly show you how we organize Industry 4.0 in general in Germany. That is beyond only asset administration shell. This is the entire organization on a national governmental level. We have a top-down. I'm not sure if you can see my I'm not sure if you can see my mouse. I will briefly show that. We have a top-down setup, and this is necessary in Germany. And it is, to say, a cultural good. And this top-down takes care of the internationalization. And you can see Korea is on the same level as China or the United States of America. Certainly, Japan is with the Robot Revolution Initiative, which was already mentioned by President Park from Cosmo, very important. But also India is kind of important for us. And on the other side, and that is very natural, the European Union. The European Union is really the core for our peace and our wealth. So we very closely collaborate with France and Italy, but also with smaller countries in Europe, like the Netherlands or others. And we have that expert network, and I mentioned it already with the machine builder, the electrical, and the software. But this top-down needs a bottom-up. This is very clear when you think of the 400,000 SMEs in Germany in the area of industry and industrial production, industrial services. So for bottom-up, we have LNI 4.0. This is a pre-competitive non-profit association. And we in this association take care of so-called use cases and test beds. And I come back to the test bed within this presentation. And the results of the, let's say, projects of these use cases that we do with small, medium enterprises in a very similar way as we heard it before from Nestfield presentation and Hanyang University presentation. These use cases are very valuable because they are kind of let's say a best practice, a lighthouse. In other words, you can do it in this way and you can achieve a benefit. You can enter into digital industrial world and by that enable new business models. This is what it is about. Creation, what you saw before is the creation of a new business model. The PhD student just explained very deeply that this machine for this injection molded bottle can be now understood as an injection machine as a service. So you don't kind of purchase a machine to produce bottles, but you get bottles as a service. And this of in a fully digital marketplace where all the data that you need to enable that business model is available and is modeled. This term of digital twin and modeling is key to success for that. What the about 150 use cases of LNI are about. To create lighthouses, and those use cases are then leveraged or bundled or put together in so-called test beds. And LNI has a unique test bed definition. And the test bed definition is about the transfer of the results of these use cases to standardization. And let me briefly, very shortly, stay here on that part of this triangle. You don't see it in it here. And there is standardization and there are normative activities. And normative activities are global and they are hardened against civil law and criminal law. So this is what we exactly need in factories, for example. While standardization is hard against civil law. Whenever, let me put it very simple, whenever there's a problem here, you can solve that with money. When there is a big problem here in your factory and a prosecutor comes, you are facing as a plant manager of an industrial plant also to be prosecuted. This is a big legal difference. And this legal difference is one of the key obstacles of Industry 4.0 in general. So we in the OT, in the operational technology, are very much aware of the wonderful and great technologies in IT. We know them. However, we have to close the gap from standardization to normative. And this is why we so intensively work on asset administration shell and other topics, which come somehow from the way of thinking of IT, but we want to make them hardened in our OT world. This takes time, but we can speed up. And this is what we do in testbed. So next slide. I hope this works. Yeah. How do we operationalize this? So in Germany, we have 26, I don't know how to get rid of this. Yeah. In Germany, we have 26, okay, better. In Germany, we have 26 so-called competence centers. They are all funded by the national government, by the German central government, by the Ministry of Economic Affairs. You heard at 2 p.m. a brief presentation of the representative of the Economy Ministry. Dr. Gröteke was giving you a 10-minute introduction. So there are 26 of those so-called competence centers, the red and the blue dots, around Germany. And all have everything with respect to Industry 4.0. So in all you find technologies like IoT, additive manufacturing, VR, AR, robotics, I mentioned already artificial intelligence, etc. This is necessary because the culture in small, medium enterprises in Germany don't like to drive very far. So you have to have something in the region. And if it comes to very special problems, let's say here, then this center will delegate to other centers to go more deep. But the first intro for the project can take place everywhere in the smallest places in Germany. This is our principle. And LNI works with all 26 together. So we can directly link all the small, medium enterprises to those centers. And by that, very little everyday life workload is on LNI. The everyday life takes place in these 26 centers. And this technology academy in Hanover is one part of that. So there we have rooms at the fairground. It's the hall 36 of the fairground, where all these events and use cases can take place. For instance, there are demonstration machines, as one you saw before. It's a full-scale production line, which is working at Volkswagen for the commercial vehicles. And they call it Campus for Digitalization. So what they mean by that is they are executing that not the normal field bus technology is connecting the components, the machines, the devices, as we heard before, but it is connected by asset administration shell and hooked up to the cloud, as you saw it before with President Park from Cosmo presentation, that the things are moving to the cloud. The software is moving into the cloud. However, you see here in industrial camera, still some processing here because it is too expensive, and it will be too expensive in the next minimum 10 years to transfer even images to the cloud to get it there processed. This might work for some images with low frequency and low rate. But in general, if you ask me for general statements, there is still an edge layer in between where processing takes place. In the fairground of the Hanover Fair, there's a big 5G so-called campus network. This campus network is very important for us because this is very interesting. It covers all providers of 5G technology. For instance, Samsung or other partners globally have devices there, have technology there where you can hook up to. And it is a private 5G network. So you might imagine that this is not a 5G network provided by KT or SK in this way. It is operated by the fairground itself. So we have a law in Germany where a certain frequency, it's 3.8 to 3.9 gigahertz, is reserved for so-called campus or private networks. So you in your factory, in your fairground, have private 5G, put it this way. You can then ask an operator like KT or SK to make it for you and to put it for you. But it is still private. They are not allowed to use your, let's say, installation for public use. It is still private. And this we have here. And we have it with many, many, many different providers. By the way, even global providers. I'm not absolutely sure, but I think also one of the large Korean providers is on that fairground, providing this private campus network. And it is really big. So it is the whole fairground plus the surrounding in Hanover. And you can ask for services from this 5G network. And now it's interesting. With the help of the 5G ASEA Association, which is an association for industrial 5G, we have a full-scale asset administration representation of this 5G network. So the entire network and all its services can be browsed, as we just saw it before in the PhD presentation of Hanyang University by this wonderful lady. And just imagine that not the machine, but the 5G network is fully represented in the asset administration shell. So you can browse all the services, let's say quality of services, etc., of this 5G network. And we will connect this 5G network with our testbed. And let me briefly go one more time to the competence centers. So here we have the competence center in Hanover. And it's part of the 26. And you see, there are not many companies involved. These are all, let's say, university partners or institutes somehow. This is, for instance, a big AI, artificial intelligence institute, very big. One of the 5, 6 big ones in Germany. And so we have a broad basis of technology and access, which is bundled in this, let's say, logo. And based on that, we can execute. So again, it covers, for instance, also here you see assembly and you see education. So this testbed has a home. It is in the fairground in Hanover in Hall 36. And we have several goals with this testbed. The first goal is the validation of the asset administration shell. This is what it is about. And you saw the illustration on the right side already in the presentation of Nestfield before. And I will go into detail of this presentation, of this illustration in the next couple of minutes. We will, by the validation of the different submodels of the asset administration shell, we will be able to support the standardization activities in IEC 63278. We will test and support and foster interoperability among all assets. And now it is important at as little cost as possible. This is exactly the same goal that Professor Hong and also President Park in their presentations were emphasizing already. For us, assets include almost everything, also the humans, beside the products, the production, the facilities, the supplies, etc., over the entire life cycle. And it also includes contracting. So what you see on the right side, and let me please again go to my laser pointer, you see an entire factory, an entire machine. You see the analytics, you see the contracting, but you also see single components. They are all connected and communicating in a semantic interoperable way with the so-called Industry 4.0 language. The digital twin, and I will come back to that later on, is a key element there. As I mentioned, 5G must be connected. We will build a demonstrator, and important for us is education and upskilling, as I mentioned already. So why do we need a testbed for that? It can be explained in this picture. We would like to ensure globally that plugging of an asset, so searching an asset, let's imagine you are a component or a technology. You enter an SME. So the SME must be able to find this new device or technology, very easy. You want to plug it in, very easy. Let's say as easy as you plug in your charger for your smartphone. And for that, we need hard normative support. So normative shall not have lock-in effects with vendors. This would be not good. So normative must be general. It must be open. So this is important. While the play, for instance, the machine that you just saw before, that is still business. There we have to ensure that the companies can earn money. So the play of an asset, this must be free business. And in Germany, we organized it in the way, as I told you before, the machine builder have all the machine domain competency. The electrical are more responsible for the connecting of the controls of the machines, and the Bitkom is responsible for the software. And what is an asset? If this thing is called asset administration shell, it must be clear what is an asset. And I like that definition down here most. Asset is an item an organization has interest in. This interest can be monetary, so you want to earn money, but it can be also different. Let's say that it is a value for you in a different way, let's say even in a cultural way. The formal definition is that everything that requires a connection for an Industry 4.0 solution. This is the formal definition. And the overall goal is the integration of an asset and the humans in the world of information. So as I mentioned before, it covers humans, the machines, the entire supply, the documents, which is so important, contracts, and many others. And what is the asset administration shell? So this excellent presentation of the PhD student, which was, the lady was talking before me, gave already some insights here, and I would like to elaborate it a little bit more. There are many, many digital twins. For instance, in biology or in chemistry or in the construction field. They are, or architecture. They are also having digital twins. When it comes to digitalization of industry or smart manufacturing or Industry 4.0, for us, the digital twin is the implementation of the digital twin. So the asset administration shell is for us the implementation of the digital twin. So digital twin for Industry 4.0, we call that asset administration shell. This is what we call asset administration shell. And it has some properties which are very important for us. It must be cross-company. It must enable multi-vendor interoperability. This is a must-have. And very important for us, it is available for intelligent and non-intelligent products. We saw before the example of Nestfield and also the Nestfield presentation and also the presentation of the PhD student, where we saw on one side the machine and on the other side the shampoo bottle or the soy sauce bottle. For us also the soy sauce bottle, which has no electronics implemented, which just has a barcode label printed. It is non-intelligent, but it can be also completely represented in an asset administration shell. That asset administration shell could cover, let's say, the material, the plastic, the PE2 plastic, which it consists of. So this would enable recycling in a full life cycle understanding. for instance, just as an example. And that brings me to this complete life cycle. It covers the asset administration shell, covers the entire life cycle of products, devices, machines, facilities, etc. It enables integrated value chains, and by that is a digital basis for autonomous systems and artificial intelligence. And this is very important for us. You might face the same situation in Korea as we face it in Germany, that that artificial intelligence, 80% of projects in the area of AI are using, or the 80% of the time is necessary for data collection and data optimization and checking the bias of the data and checking the validation of the data. With asset administration shell, we will have trustful data with IT security where our AI applications can easily build up on. So the digital twin, I gave already that definition, is the implementation for Industry 4.0 of the asset administration shell. And we saw already that picture before. And I would like to a little bit emphasize on it. This is taken from the RAMI model, and this is the life cycle of any industrial area or thing. It starts with development and it goes via the maintenance and usage all the way to the recycling, which is not shown here. And there are already several implementations existing, and I will come back to that later on. So we have the UML, we have OPC UA for industrial production and machines. Certainly we need automation ML, but also RDF for the analytics is already there. The most important is that security by design is ensured. The highest level of IT security must be there, and we also believe that this can be only guaranteed not in the cloud services can guarantee IT security better than on-premise computing. There are 3 types of asset administration shell. And I would like to stick to this a little bit in the next 2 slides. There is a so-called passive asset administration, AAS. There is a so-called reactive AAS and a so-called proactive AAS. The passive AAS covers several layers of this RAMI. And you see them here on the y-axis. So it is the asset layer itself. So again, an asset can be also a human. Let's say we have a worker that has a special training for welding. Let's say this worker is qualified for welding a special upside down. Then this worker has a representation for all his wonderful and valuable qualifications. Then there's an integration layer, communication was already discussed. Information layer is semantic information models. That includes properties, parameters, variables. The functional layer, let's say drilling, we had extrusion, plastic extrusion before, whatever it is. And then there's also a business layer where the contracting, micropayment, etc. come into place. And you see already in this illustration that not all types will cover everything. And this is good and okay. For all types, we have use cases. So we need all types to get it cost effective. And I would like to emphasize on what the PhD presentation was already about. And I highlight here in the center the submodel. I would like to briefly become technical. What you see here looks complicated. But honestly, it is not complicated. It just looks complicated. In general, what you see is when you come from the programming, from the software development, what you see here is a class. So this is the class name. This is the way how software developers program in C++ or in Python or in Java or in C#. Everything looks always this very same. So you have a class name here. Oh, I don't know what happened. There's something coming up. I'm sorry for this. So there's a class name here, and you have methods here. And these methods are implemented, and then you have attributes. And this is it of this entire class. So a submodel class has some methods that you can call and get an answer from. For instance, it's identifiable. It has semantics. It has kind. It has data specification. It's qualifiable. And this is what it is about. It sounds really, for non-technical people, this sounds very complicated, I agree. And please excuse that I briefly explained some technical things now. But it is less complicated as before, mentioned before. And Nestfield presentation today, and also the wonderful PhD presentation from this lady from Hanyang University. Again, thank you very much for this excellent presentation that you gave. Showed how these submodels can be implemented. E-class is one very good way to implement those and have those submodels. And you see some submodel elements and properties and the property definitions in IEC 61360. And I will come back to that later on. And for instance, we had the presentation just before about energy. So energy efficiency, for instance, just one example for submodels. It contains the energy saving mode. You know that from even from your household device, you know how energy compliant everything is. It can contain the cumulated energy or potential energy savings. Let me continue a little bit with the submodels because they are so important. We are talking about properties, variables. We are talking about events that can happen with a machine, with a building, with a factory, a shop floor. We need references. We have to refer to other submodels, to other asset administration shells. This is shown here. So we have to have the ability to refer the asset administration shell, which is a collection of all the submodels in that machine. But to the top, it is just one asset administration shell of the plastic extrusion machine that we saw before from Nestfield. And that machine must be able to connect to an ERP system, possibly to a contract or to the maintenance department. So we have to have also capabilities. And very important, we need arrays. So we have to have a set of properties that can, like a collection. And we need entities for describing the composite components for Industry 4.0. And specifically, this means that there will be submodels for identification, for technical data, for operational data, and that can cover both our machine operators, but also the maintenance department, and most importantly, for the documentation. If we start really with the documentation, we will gain very quickly a win-win and have low-hanging fruits in taken care of. Imagine that our maintenance department has all documentation at hand on a tablet or any other device when it needs it, and no second anymore has to look for it. This would be such a big low-hanging fruit financial win. And let me briefly go to the already existing implementations for these information models. In the German Machine Builder Association, they work very close together with OPC Foundation and using OPC UA technology. They have so-called companion specifications. So there's a label made up. It's called UMATI. And in this screenshot here on the right side, sorry, it's not good screen quality, but no problem. I think you see how you can browse all assets in the collection. So you can browse those. You can get all the information which is listed on the left side that you require. So this is existing for the machines itself. It is existing for tooling, for robotics, for industrial vision, for scales, for the general PLC, the so-called open PLC, and it is existing for some more kind, let's say, special tooling machines in areas like plastics or wood. And then you can, in a standardized way, retrieve information from those machines, although they are coming from different vendors. So this is called UMATI. And E-class, I would like to give again the relation also with respect to the business behind it. Let's say you want to have a hole somewhere. You call for the service drilling. The service drilling has several properties. Let's say the diameter of the hole or the depth of the hole. But it also has the property price or delivery date. And here, this looks very complicated on the right side. But these are the AAS submodels for that. And from a software developer, computer perspective, this is not so complicated as you might think. It has this identifier. Everything will have an identifier. This is the class name, the submodel elements. This is then the attributes that you need for that, and some software development things around it with these parentheses. And all of a sudden you have described this kind of complex service drilling in a complete software representation as a digital twin. And by that you can handle it. And you can automatically come to that service and bring it together. And that brings me to this language. And I would like to briefly stick to that language. A natural language consists not only of words and grammar. There's one more thing, and that is very important. These are the dialogue sequences. We are talking to each other. We are in a dialogue. In the end, every exchange is somehow also a negotiation. We are talking to each other in the room and explaining to each other what we think. We are negotiating with each other. There are design, and for this way of communication, there are design principles and rules. They exist. By our linguistic scientific colleagues, this is researched since several hundred years. And this way, this setting can be transferred to Industry 4.0. We have a vocabulary for Industry 4.0. These are the asset administration shells. And there is a structure of a message. And that is the VDI 2193-1. It's the concept of an Industry 4.0 language and message structure. And by that, with the -2, we can come to a bidding process. So machines, components in a machine, logistic devices, everything like this, even the technical building equipment, the shop floor, the entire plant, the maintenance department can automatically ask for services and go in a technical bidding process. So automatically a service can be ordered and later on paid, possibly with a micropayment, in this interaction protocol process. Very comparable to a dialogue sequence of a human communication, let's say in a room. This is exactly what the testbed will try to work on, to get in this general level on all areas and let me go back, on all areas and levels of interaction in a factory. I would like to go back to this implementation along the life cycle. Lots of stuff exists. Automation ML fully provides asset administration shell. The presentation before by the PhD student of the Hanyang University, or Kitech, I think it's Hanyang or Kitech University, I'm not so sure. Oh, possibly it's embarrassing for me. I think you are with Kitech University. So sorry for that. That was my confusion. So the PhD student of the Kitech University presented already an example for that. So I will not go into details. The Asset Administration Shell Explorer is open source on GitHub. Here is the link. And President Park and Professor Hong has the slide for this, so you can have the slides. So here you have an explorer where you can plug asset, you can browse and plug asset administration shells. There are REST API implementations already in JSON existing. Also, this can be found on that GitHub. So even the W3C protocols are supported. I showed you already with the browser here that OPC-UA and UMATI supports the asset administration shell. So the so-called companion specifications can be browsed. And for the analytics part, which is in our opinion very important, if you want to do closed loop control over the entire life cycle, RDF implementations supporting the asset administration shell exist already. Let me briefly go over the different standardization activities that we observe globally. So we have the IEC 63088 for the RAMI. And there we have the Joint Working Group 21 of ISO and IEC on that. We have lots of activities in Working Group 22 and 23 and 24. And in Korea, Professor Hong from Hanyang University is the conveyor. We have now the 62832 new work item proposal since about 1 year, where also Professor Hong is highly involved. In the JTC1 activities, we have the AG11 with the digital twin. We found that IEEE is also working on that more in the standardization area with system architecture of digital representation. And we have the ISO AW1 23247 digital twin framework. So it seems complicated, but be ensured all are synchronizing themselves, each other, and there is synchronizing activities. I am at the end of my presentation. It works, I think. Yeah. Thank you very much for having me, for listening. And let me summarize it in this way. Germany is very, very glad and proud and happy about the very trustful and close collaboration between Korea and Germany on digitalization of industry. We are available for your questions, and we are very happy about the trustful and fruitful collaboration, which we will continue with the signing of a memorandum of understanding on November 25th, where our ministers will be present. Thank you very much, and I return the presentation to you in Korea. Thank you very much. So the next speaker will be Jens Geiko. He is the CEO of the Standardization Council Industry 4.0.
Talked about questions, and we will collect all the questions from the chat box, and we will ask the question during the Q&A session. Next up, I'd like to introduce you another German speaker. There is the Standardization Agency, and Dr. Jens Geiko will give us a presentation about standardization, and he will make a presentation during the 15 minutes. Would you please begin?
Hello. Good afternoon to Korea. Thank you very much for the opportunity to give a presentation here. So again, thank you very much for having the opportunity. As already announced by Dominik Romus, my name is Jens Geiko. I'm the Managing Director of the Standardization Council Industry 4.0. And you have seen already on the previous presentation sometimes the logo of the Standardization Council. And I will explain a little bit on our activities. But I have to say that the previous presentations have been very well structured, and you have seen many of the pictures and diagrams already before. So I will try to link these technical concepts to our standardization activities, and also to figure out where I see the potential for closer cooperation between Korea and Germany. And I'm very happy about that. First of all, the Vision 2030 of the German Platform Industry 4.0 consists of 3 pillars. And this has been already shown before in this conference today. We have the 3 pillars of autonomy, interoperability, and sustainability. And of course, this strategy is very important also to guide the direction of our standardization activities. So we use this Vision 2030 as a high-level input for our standardization strategy. And here we need to consider both the technical aspects of, for example, interoperability, autonomy, and so on, but also the non-technical aspects. What does it mean? Non-technical aspects include, for example, the legal framework. Because if you want to offer a product or a service in a market, you need to fulfill the legal requirements in this market. And here it is important that the standardized technical solutions we described as our standards can fulfill these legal requirements in different regions of the world. And of course, in Germany, we know quite well about the legal requirements in Germany, and we know reasonably well in Europe, but we are not experts for the legal requirements, for example, in Korea or other regions of the world. And for example, there is regulation on data protection. And if you offer a service using the asset administration shell, you need to fulfill these regulatory requirements on data protection if this is applicable for your service you want to offer. And therefore, our task is to design the asset administration shell and all the ecosystem around the asset administration shell in a way that you can offer your service worldwide. This triangle was also shown already by Dominic, and it shows the overall cooperation between the Platform Industry 4.0, Labs Network Industry 4.0, and the Standardization Council Industry 4.0. In particular, the cooperation between the Labs Network Industry 4.0 and the Standardization Council Industry 4.0 enables the small and medium-sized enterprises to access to the latest draft of the standards and also to contribute to the standardization work. This is very often a big challenge for standardization activities to include the small and medium-sized enterprises, because very often they are not able, or they think they are not able, to contribute to international standardization. But when they are active in a pilot project of the Labs Network Industry 4.0, they have access to the latest draft of the standards, and also the results of these pilot projects will be directly included into our standardization activities. And by this, we establish this know-how transfer in both directions. We call it agile standardization because it's a kind of agile cycle. We do some specification at the standardization side, and some implementation and validation at the Labs Network Industry 4.0 side, and then a feedback of the findings of these implementations and pilot and validation tests. And by this, we have very good progress of our standards, and also we can include the know-how from many companies. So therefore, a few years ago, when the theme of Industry 4.0 came up, these requirements have been identified, and that was the reason to establish the Standardization Council Industry 4.0. And on this slide, just a moment, oops, sorry. You can see here on the left side, you can see that this is a joint project from the DKI and DIN. These are the two national committees for the standard ISO and IEC. It's also supported by the Platform Industry 4.0 and by the Industry Association VDMA for Machinery, Bitkom for ICT, and ZBI for Electrical and Electronics Industry. And so we have a wide support from all these relevant industries. And what are our main tasks we are dealing with? Well, as already explained before, Industry 4.0 requires interoperability between the IT level, like the enterprise resource planning and so on, and the OT at the shop floor level. And traditionally, the standardization for the shop floor level is done at international standardization organizations like ISO and IEC. And on the other hand, the standardization for the IT is typically done in consortia standards, like, for example, W3C for the Internet standards, to give one example. And here, this is not a competition among these organizations. We need to manage the cooperation and collaboration among these organizations, because we need both in the end. So this is one of our tasks. The second one is to discuss our concepts on the international level, like I'm doing today here, and I'm very happy that we could establish this very good cooperation with Korea in the recent 2 years. This is also one of our tasks. The next one is the agile standardization. As I explained before, we do this together with the Labs Network Industry 4.0. And finally, we have a so-called orchestration to implement all these activities. One of the central documents to orchestrate the implementation is our Standardization Roadmap. This roadmap was, the latest version of the roadmap was published in July this year in an international event. And I know that some of you have joined this event. And here you can see the link to this roadmap, and you can download it in English as well. And in total, there are 115 recommendations for the standardization activities. Also, you can see a link for keynote speech of Mr. Teigler, Managing Director of DKI. Well, on the asset administration shell, many things have been said before, so it's quite easy for me, and I can focus on a few specific items. As we have heard before, the asset administration shell is a digital twin of an asset in the domain of the smart manufacturing. And this requires some standardized activities. So we have in general a kind of container format with a standard format, and then we have different technology dependent formats like, for example, OPC UA and Automation ML, as we have seen before. Standardization has started beginning of this year at ISC TC65, and here you can see a picture from the kickoff meeting. It was just before the Corona crisis emerged, and maybe you can see Professor Hong also could join this meeting, and we have been very happy that we could have a face-to-face kickoff. And since that time, the group is very active in web meetings, and the committee draft is under preparation or will be launched soon. As we heard also before, it's more than just the data format. You also need the interaction models. And by the use of the semantic properties, you can achieve a kind of translator between the different languages of the Industry 4.0. Or to say, basically, we don't need these different languages because we have an interoperable machine readable format, and we achieve the semantic interoperability. We have heard about the semantic properties, and this will play a very important role. And we have heard also there is not just one repository for semantic properties, but they are different. And namely, there is at IAC, there is a common data dictionary, IAC CDD, as it is described in the IAC 61360 series, and also other standards. And besides that, there is a consortia-based repository called eClass. And maybe there will be further repositories, or there could be even properties defined between, for example, business partners, for example, a manufacturer and an integrator and an operator of a plant. Even if they like, they can define their own properties. Of course, you have different speeds for the implementation for these properties at the different organizations, and also you have differences in the international acceptance and the stability. But in the end, all these repositories, they form the vocabulary for Industry 4.0. And here again, it's not a competition among these repositories, but we need a cooperation. And this is currently one activity we started. So since the beginning of this year, there is a close cooperation project between eClass, ISO, and IAC. And we are preparing here a project to bring closer together these two repositories. Well, we heard already about the mapping to different technologies like Automation ML, OPC, and so on. And this is also quite important for our activities. So this brings me to the conclusion of my presentation, because here I summarize our activities, and I think these activities, I give directly a link to a potential closer cooperation in the future. First of all, as we heard, the first the -1, so the first standard of the IAC 63278 series is launched, but there will be further standards of this standard series. For example, on the interaction models, on the infrastructure service, on mechanisms for security, and so on. And this is something where we need the international cooperation to successfully start and develop these standards. As a second activity, we need the extension of the repositories for semantic properties. And this includes a seamless coexistence of the different repositories. As I mentioned before, for example, a cooperation between the IAC CDD and the E-class repository. And also here we need support from the different countries, and I think this is a good chance for cooperation. Next one is the modeling of aspects of assets, these so-called submodels, as we heard before. And here there is one example, the digital nameplate. The digital nameplate is one example for a submodel, containing all the information we have today on the physical nameplate of a product. And here currently there is new work item proposal is open for Belut at IAC Subcommittee 65E. And here also we would like to start a closer cooperation. And I think this is a quite interesting project because here we have the technical aspects, how to model the data in a submodel. But also we have the non-technical aspect because it would be ideal if this digital nameplate can be accepted in many regions of the world by the government. Next activity is the link to Gaia-X. So this morning we saw the presentation by Dr. Gröticke on Gaia-X, and as he mentioned, Gaia-X will use the concept of the AAS, and here we need to define this, how this looks like in detail. And as already mentioned before, the mapping to different technologies. And in my eyes, these are potential starting points or for further cooperation, and I look very much forward to continue this cooperation with you. And if you have any question, please feel free to contact me. Thank you very much.
Thank you for your presentation. Dr. Jan Skyko, thank you for your wonderful presentation. We really appreciate it. We began from 2 p.m. and it has been 4 hours to operate and have this forum. And we are very punctual. This is about 6 p.m. I think it's 10 p.m. in Germany. We are about to finish at the scheduled time. I think that's very lucky. About 300 participants are joining us online. And I really appreciate your participation. And for the new technology of AAS is getting a lot of attention. Thank you very much for your the support and interest. I think all the technologies secured by the agency will be distributed to the SMEs, and they will carry out many different projects to do so in the future. My biggest concern is that after listening to this seminar, you might say AAS is so complex, it's so daunting. I encourage you not to do so because we are developing many manual and many training sessions about AAS, so please be encouraged. It can be difficult and complex, but once you have tried, it's not that much difficult and not that much complex. It's very good technology. So we have 2 experts from Germany. Thank you for your wonderful presentation and joining us. Thank you for joining us. I sincerely wish to see you after the end of the coronavirus. We want to see you in Rio. We can visit each other, and we expect more close cooperation will be made in the future. I think that's the conclusion of today's event. Thank you very much.
Also, thank you very much to Korea for having us, and all the best. Thank you very much.
Thank you. Bye-bye.